So, Jai Jai Jagannath, welcome to More Physics. This is lecture number 4 of capacitance. Here we will start with discussing the force between two parallel plates in a capacitor. So, there are two plates. This is first plate, this is second plate. So, on these two plates, one is positive charge, another is negative charge, and distance of separation is equal to d. So, now you see, suppose I will take a point P. So at P point, what is the electric field intensity due to the first charge sheet? So you know, using Gauss law, we had already proved that electric field intensity at any point due to a charge sheet is equal to what? Sigma by 2 epsilon naught epsilon r. So what is sigma? Sigma is equal to charge per unit area. Charge is Q divided by, if the area of the plate is A, so Q by A is equal to sigma divided by 2 epsilon naught epsilon r, and that is equal to Q by 2 epsilon naught epsilon r into A. And since this is positive plate, the electric field is away from the positive charge plate. So this is the direction of the electric field intensity. And you see, we know when any charge particle is brought inside an electric field, that charge particle will experience a force. So now this negative charge plate is coming under the electric field produced by the first plate. So this negative charge particle or plate will experience a force. So what is that force? Force magnitude is equal to the charge magnitude into electric field. If we write in vector, then I can write the F is equal to minus Q into E. So that is equal to Q into minus E. And here you see direction of force on the second plate is equal to negative of the direction of electric field. So electric field is towards right. So the force on the second plate due to first plate will be towards this. So this is can be written as force by 1 on second particle. So what is the magnitude of this force? The magnitude of force, that is force by first plate on second plate, is equal to Q into magnitude of E. So that is equal to Q. What is the magnitude of electric field intensity at P? This is the value. So that is Q by 2 epsilon naught epsilon r into A. So that implied force by first plate on second plate is equal to Q square by 2 epsilon naught epsilon r into A. So this is the force. And since this positive charge is attracting the negative charge, so this force is definitely a attractive force. Similarly, the plate A is coming under the electric field produced by the second plate. So this A per plate will also experience a force towards negative charge. You see, at A point, what is the electric field intensity? Let us say I am taking this is here, which point? This is the A is the area of the plate. Let us say this is M point. So at M point, electric field is equal to, due to which sheet? Second sheet is equal to same, sigma by 2 epsilon naught epsilon r. And since it is the negative charge plate, the electric field is always towards the negative charge plate. So this is the direction of the electric field intensity at M point due to second plate. Now this positive charge plate Q is also coming under the electric field produced by the second plate. So now this positive charge Q will experience a force. So what is that force? That force is taken to be force by second plate on first plate is equal to the charge of the first plate, that is Q, into electric field intensity at M point, that is EM. So if you calculate again, you will get Q square by 2 epsilon naught epsilon r into A. So this is the force of attraction between the two parallel plates. So now you see these two forces are attractive in nature. So this is a force by second plate on 1. So these two forces are attractive in nature, so they will be attracted each other. But there is a dielectric medium inside the plate. So that dielectric medium prevents the sticking of these two charged plate. Okay. Now see, now we will discuss combination of capacitors. So what is the combination of capacitors? You see, suppose you are doing a project, electrical project. So for that project, you need what capacitance? 0.5 microfarad capacitance. You need to do the project. But in the market, so in market, 2 microfarad capacitor is available. 2 microfarad capacitor is available. So how will arrange these 2 microfarad capacitors so that you can get 0.5 microfarad? So that means we have to combine these 2 microfarad in such a way that I will get 0.5 microfarad. Similarly, suppose I need 0.5 microfarad as well as 6 microfarad. But in the market 2 microfarad is available. So how will you rearrange so that we will get either 0.5 or 6 microfarad? Okay. So according to that, we have to combine the capacitors in various ways. One is series combination, another is parallel combination. So first we will discuss what is capacitors in series. Series combination of capacitors. You see, suppose I will take n number of parallel plate capacitor. So the first capacitor capacitance C1, this is C2, up to we will take n number of capacitors. So they have to connect in series. What will do? So in the second plate of the capacitor will be connected to the first plate of the second capacitor. Similarly, the second plate of the second capacitor will be connected to the first plate of the third capacitor. In this way, we have to connect all the capacitor, and this connection is called series connection. In the series connection, if I will give a supply voltage of V, what will happen? The charge will start flowing from positive terminal and negative terminal. Let us say the charge sent by the positive terminal is Q, charge sent by the negative terminal is minus Q. And you see, this positive terminal is directly connected to the first plate. So since it is directly connected, so whatever Q is sent by the source, that will deposit on the first plate. Similarly, this minus Q charge will come to this plate. So here the charge will be minus Q. Now you see, this plus Q, and there is a dielectric medium, insulating medium. So what will happen? This Q will induce a charge of minus Q on this plate. But you see, this plate and this plate both are electrically isolated. Why? Because before this plate there is insulator or dielectric. After this plate there is also insulator, that is dielectric. So these two plates are electrically neutral, isolated. So if it is electrically isolated, the total charge of the two plates is 0 initially. But here in this plate minus Q charge is induced. So this minus Q, and definitely this plate must possess plus Q, so that plus Q minus Q totally charge is equal to 0. Now again this plus Q will induce minus Q on this plate. And this plate are electrically isolated. Total charge will be 0. If this is minus Q, definitely the second plate will possess plus Q charge. In this way, it is minus Q, it is plus Q. So in this way, charge will be distributed. Now, what is the conclusion? What is the conclusion? You see, in this series connection, the charge across each capacitor remains same. So I can write in series, charge across each capacitor, remains same. This is the characteristic of series connection. But what will happen? The potential difference across each plate of the capacitor depends upon the value of the capacitance value. Suppose the V1 is the potential difference across first plate, V2 is the potential difference across second plate. In that way, Vn is the potential difference across nth capacitor. And we know V is equal to Q by C. This is general formula. So here you see the charge are distributed equally in all the plates. So in this series connection, Q remains same. If Q is remains same, then the potential difference is inversely proportional to the capacitance because Q is constant. So that means the potential difference across V1 is to potential difference across V2 is to the potential difference across V3 C3 is equal to V1 is nothing but 1 by C1, 1 by C2, 1 by C3. That is potential divides with inverse ratio of the capacitance value. Okay. Now we know as per Kirchhoff's voltage law, you have read in class 10th physics, as per KVL, what is Kirchhoff's voltage law? The total supplied voltage, that is V, is equal to the sum of voltage across each capacitor, across each element. So I can write V is equal to V1 plus V2 up to Vn. But what is V1? V1 is nothing but charge by capacitance Q by C1 plus Q by C2. In this way, you will get Q by Cn. This is the total supplied voltage. Okay. So now, what is equivalent capacitance? Here you see there are n number of capacitors connected in series. If instead of n number of capacitor, I will take a single capacitance whose capacitance value is Cs, and this whole capacitor is connected to this source with potential difference V. Now the whole capacitors are now converted to a single capacitor, and that single capacitor will be connected to the same voltage. What will happen? So here initially the charge drawing by all the capacitor is Q. Here also the single capacitor is drawing charge Q. So here charge of the capacitor is Q and capacitance value is Cs. And what is the potential difference across this capacitor? You see this positive terminal is connected to this plate, negative terminal is connected to this plate. If the potential difference across this source is V, then potential difference across this capacitor is also V. Then what is the relation between V, Q and Cs? I can write V is equal to Q by Cs. So in this place, in V I can write Q by Cs, which is equal to Q by C1, Q by C2. If I'll take common Q, it is 1 by C1, 1 by C2 plus 1 by Cn. So this Q cancel. So I will get 1 by Cs is equal to 1 by C1, 1 by C2 up to 1 by Cn. So this is the formula of equivalent capacitance. So here I can write here Cs is equivalent capacitance in S stands for series, in series connection. Okay. So now 1 by Cs is equal to this. So now let us take suppose there are two capacitors. So this is C1, this is C2. This is connected across A and B. So I have to find what is the equivalent capacitance across A and B. It is series connection. So I can write 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So that is equal to LCM is C1 C2, C1 plus C2. So from this I can write the equivalent capacitance is equal to, just take the ratio, that is C1 C2 by C1 plus C2. For the numerical, when you will solve the numerical, particularly when there are two capacitors are connected in series, you can directly write the equivalent capacitance is equal to C1 C2 by C1 plus C2. Suppose there are three capacitors. Capacitors C1, C2, C3. Then what is the equivalent capacitance? So equivalent capacitance is equal to 1 by Cs, 1 by C1, 1 by C2, 1 by C3. So just take add this. So you will get C1 C2, C2 C3, C3 C1 divided by LCM is C1 C2 C3. This is 1 by Cs. So that implied Cs is equal to C1 C2 C3 divided by C1 C2 plus C2 C3 plus C3 C1. So don't try to remember this formula, because always remember this formula. Okay. So now interesting question is that suppose there are two capacitors. One is 6 microfarad, another is 3 microfarad. It is connected between A and B. Question is find the equivalent capacitance across A and B. So what is the formula? For two capacitance it is C1 C2. C1 C2 by C1 plus C2. So here C1 is equal to 6 into 3 by 6 plus 3. That is equal to 2 microfarad. So what is the conclusion you see? There are two capacitance, 3 and 6. But net capacitance is 2. So that means in series connection, the total capacitance or net capacitance, which is 2, is less than the lowest of the individual. So here out of 6 and 3, which is the lowest? 3. But our equivalent is getting 2. So the net capacitance is less than the lowest of individual value. That means in series connection, net capacitance decreases. Suppose you want to get less capacitance, then in that case, what will do? You will connect in series. Suppose you see there are two capacitors, C and C. So what is the equivalent capacitance? So equivalent capacitance is equal to 1 by C1, 1 by C2, that is 2 by C. So that implied equivalent capacitance is equal to C by 2. If there are two identical capacitance, then equivalent capacitance is individual capacitance value divided by 2. Similarly, suppose there are three capacitors, C, identical capacitance. Then what is the equivalent capacitance? It is C by 3. In this way, if there are n number of capacitance connected in series, the equivalent capacitance will be C by n. So now I think you got the answer what I had told you. There are in the market, there are 2 microfarad capacitance is available. How will it produce 0.5 microfarad capacitance? So definitely 0.5 is less than 2. So in that case, we will go for which connection? Series connection. Now see, this is 2 microfarad available. I want to find 0.5 microfarad. If I'll take 4 capacitor of 2 microfarad, then the equivalent capacitance will be C by 4. There are 4 identical capacitance. That is C is equal to what? 2 microfarad divided by 4. That is equal to 0.5 microfarad. So our answer, our problem is solved. Okay, so if we will consider 4 capacitors of 2 microfarad each, they are connected in series, we can get 0.5 microfarad. Now, let us solve the example this. So there are two capacitors, 8 micro, 9 microfarad, connected in series to a source of EMF 12 volt. Find equivalent capacitance across A and B. So in across A and B, the two capacitors are connected in series. If I find the equivalent capacitance across A and B, it is nothing but C1 C2 by C1 plus C2. So that is equal to 18 microfarad into 9 microfarad by 18 plus 9. So if we will calculate, I think it will come 6 microfarad. Okay, 6 microfarad. This is the equivalent capacitance. You see, net capacitance decreases. So net capacitance is lower than lowest of individual. Okay, so I have already discussed this. Then what is the charge across each? So charge across each means this total, you see, this is your A terminal, this is your B terminal, this A and B is connected to the source of 12 volt. And what is the equivalent capacitance? We have already got 6 microfarad. Now the capacitance value is equal to 6 microfarad. And voltage across A and B, VAB, it is directly connected across these two terminals, that is 12 volt. Now what is the charge across A and B. Charge across A and B is how much? So what is the formula? C is equal to Q by V or Q is equal to CV. So I can write QAB is equal to CAB into VAB. So that is equal to 6. Capacitance is 6 microfarad into voltage is 12 volt. 12 6, that is 72 microfarad into volt is equal to coulomb. So this is the charge given by this source. Okay, and this 72 microcoulomb will store in C1 as well as C2. So charge across first capacitor is also equal to charge across second capacitor, which is equal to 72 microcoulomb, because in series connection charge remains same. So I got this is the answer of second bit. Come to third bit, potential difference across each capacitor. So here charge is equal to what? 72 microcoulomb. Here also 72 microcoulomb. Then what is the potential difference across this first capacitor? What is the potential difference across second? So V1, I can write it is Q1 by C1. So Q1 is equal to what? 72 microcoulomb by C1. C1 is equal to 18 microfarad. Micro cancel. So it is 4 coulomb by farad is equal to volt. So this is the voltage across first capacitor. This is V1 is equal to 4 volt. Then what is V2? So V2 can be written as Q2 by C2. Q2 is equal to 72 by microcoulomb by C2 is equal to 9 microfarad is equal to 8 volt. Or you can say the total supplied voltage V must be equal to V1 plus V2. So what is the total supplied voltage? 12. What is V1 already have got? 4. So from this you can also calculate V2 is equal to 12 minus 4, that is 8 volt. Next, energy stored across each capacitor and total energy stored. So now we will see what is the energy stored in the first capacitor. What is the formula? Half into C1 V1 square. So half into C1. C1 is equal to 18 microfarad into V1. V1 is equal to 4 volt. So now if you will calculate, just multiply this, what result you will get? You will get, I think, 144. Yes, 144 microjoule. This is the energy stored. You can also calculate the energy stored by formula half V1 Q1. That is half V1 is equal to 4 volt. Q1. What is Q1? Q1 is 72 microcoulomb. So that is equal to 144 microjoule. Then what is the energy stored in the second capacitor? You can write it is half C2 V2 square, half C2. So what is C2? 9 microfarad into V2. So what is V2? V2 is equal to 8 volt, 8 square. So that is equal to, just multiply U2, you will get 288 joule. Okay, so this is the energy stored in the second plate. Now we will find what is the total energy stored by the all the combination. You see, for total energy stored is equal to half into total capacitor, that is equivalent capacitor, CS into V square, that is half into CS. What is the equivalent capacitance? We have already got 6 microfarad into voltage. So here what is the potential difference? 12 square. So if you calculate, I think it is called 3 into 144. So it is 432 joule, microjoule. 288, that is microjoule. Microfarad was there, so microjoule. Okay, so now you compare, you see U is equal to, if I will take U is equal to U1 plus U2. So what is U1? 144 microjoule. What is U2? 288 microjoule. If you will add this, you will get 432 microjoule. Then fourth bit, energy stored across each and total energy stored. Okay, we have already got. Then fifth bit, energy sent by the source. So energy sent by source, that means what is the work done by the battery? Work done by the battery is equal to V into Q. What is the battery voltage? 12. And what is the total charge given by the battery? 72 microcoulomb. So if you multiply, you will get 864 microjoule. Now see, this is the energy sent by the battery. That is 864 microjoule. But what is the energy stored? Energy stored, total energy stored in the capacitor is equal to what? 432 microjoule. Then a battery is providing 864 microjoule. Out of this, 432 microjoule is saved by the capacitor. So remaining energy, what is the remaining energy? Remaining energy is equal to total energy sent is equal to 864 microjoule. Energy stored is equal to 432 microjoule. So that is equal to 432 microjoule energy. It is, this energy is lost. This energy is lost. So this energy, when so how this energy is lost? You see, this battery is connected through what? Connecting wire. So in this connecting wire, some energy will be lost. That means when charge will flow, current will be established. So during that current, there is some heat energy produced according to Joule's law of heating effect. So here, this amount of energy is lost in the form of heat energy. In the form of heat energy. Now, parallel combination of the capacitor. Suppose you see, this is first capacitor, this is second capacitor. In this way, there are n number of capacitors. So this capacitance value is C1, this is C2, let us say this is Cn. And you see, all the first plate of all the capacitors are connected to a single point. Let us say this is A. All the second plate of the capacitors are connected to another single point, let us say B. And here in this A and B terminal, I will connect a source whose potential difference is V. So now what will happen? So this is called parallel connection. Okay. In parallel connection, what happens? If this is the EMF, if this is a source, the positive terminal voltage, if it is V, the negative terminal voltage is, if it is 0, then what is the potential difference? V minus 0, that is V. And this positive terminal is connected to A point, then what is the potential at A point? V. This 0 volt is connected to B point, then what is the potential at B point? 0. And this first plate of the first capacitor is connected to A and second plate is connected to B. So if this is V, then this first plate potential is V, second plate potential is 0. That means here also this plate is connected to V. So here potential is V, the second plate potential is 0. Here also V, here it is 0. Then what is the potential difference across each capacitor? So potential difference across each capacitor is V minus 0, that is V. Here also V, here also V. So that means what is the conclusion? Conclusion is that potential difference across each capacitor is same. But in series connection, charge remains same. But in parallel connection, potential difference remains same. And you know, the charge is equal to what formula? Q is equal to CV. Since V is constant for all the capacitors, so I can write charge will be distributed according to their capacitance value. If capacitance is more, it can store more charge because V is constant. Okay, so that means charge divides directly with capacitance. So I can say the Q1 is to Q2 is to Q3 is equal to C1 is to C2 is to C3, like this. Okay. So now we'll find what is the total charge given by the source. Let us say total charge is equal to Q. This side is Q and this negative side is sending minus Q charge. So when this Q comes to a junction, it will be divided according to their capacitance value. Suppose the first capacitor stores charge Q1, second Q2, third Q3. So now we will put as per KCL, Kirchhoff's current law. What is Kirchhoff's current law? Total incoming current is equal to total outgoing current. Current is nothing but the flow of charge. So total incoming charge to this A point is equal to Q. Total outgoing charge through all the capacitor is what? Q1 plus Q2 up to Qn. So that implied Q is equal to, what is Q1? So charge through the first capacitor is equal to, what is the capacitance value? C1. What is the voltage? V. So Q1 is equal to C1V. Similarly, what is Q2? Q2 is equal to C2 into V. Similarly, what is charge across this nth capacitor? So here capacitance is Cn, voltage is V. So this is the total charge. But what is equivalent capacitance? Instead of n number of capacitors connected across A and B, if I will connect a single capacitor with same terminal A and B and let that capacitance value is Cp. So this Cp is equal equivalent capacitance of all the capacitors connected in parallel. And now you see this A and B is connected to this source. So here also A and B is connected to same source V. But instead of n number of capacitor, we are taking a single capacitor. Same source, and this source, here this source was sending what charge? Q. Here also it is sending to same charge, that is Q and minus Q, to this capacitor. So here charge across this capacitance is equal to Q. And what is the voltage across this capacitor? It is directly connected to positive terminal. It is directly connected to a negative terminal. So the potential difference across these two plates is equal to V. So I can write here what is the relation between Q, V and Cp. So I can write Q is equal to Cp into V. So here in place of Q, write down, in place of Q, we write down Cp into V is equal to, here V, take the common. So it is C1 plus C2 up to Cn. So that implied V cancel. So Cp is equal to C1 plus C2 up to Cn. So this is the equivalent capacitance in parallel connection. So here it is just like a resistor connected in series. In 10th class you have read resistors connected in series. So the equivalent resistance is equal to R1 plus R2 plus Rn in series connection. But here it is just reverse in case of parallel connection. Okay. So you see, just example. Suppose C1 is equal to 6 microfarad. C2 is equal to 3 microfarad. It is connected across A and B. This is in series connection. In series connection, we had got 6 into 3 by 6 plus 3, that is 2 microfarad. But if the same capacitor is connected in parallel, that is 6, 3 microfarad, then what is the equivalent capacitance in parallel connection? 6 plus 3, that is 9 microfarad. Now see, this net capacitance, that is 9 microfarad, is greater than the highest of individual. Highest of individual is 6. So capacitance is more than 6 microfarad. It is also more than 3 microfarad. So what is the conclusion? Conclusion is that net capacitance increases in which connection? Parallel connection. In parallel connection. So I had given an homework, that is I had told, so in the market 2 microfarad is available, but we have to make it 6 microfarad. So what we'll do? Just connect these 2 microfarad in parallel connection. So you will get this is 2, this is 2, this is 2. So net capacitance will be 6 microfarad. Okay. So this is about the parallel connection. So now in the parallel connection, how charge is distributed? Suppose there are two capacitors C1 and C2, both are connected in parallel. Total charge is equal to Q. So out of this Q, Q1 is stored in C1 capacitor, Q2 is stored in second capacitor. Suppose we know the C1, C2 value and we know the total charge, then how can you find Q1 and how can you find Q2? That is charge distribution. So you see, so these two capacitors are connected in parallel. So what is the equivalent capacitance? So equivalent capacitance is nothing but Cp is equal to C1 plus C2. Cp means equivalent capacitance in parallel connection. That is C1 plus C2. So here the voltage across both are same. So here also voltage is same. So the total charge given to the two capacitor is Q. So here total charge is equal to Q. Okay. So I can write what is V? What is V? So V is equal to Q by total capacitance, that is C1 plus C2. So this is your V. So now I want to find what is the charge across this first capacitor. So what is the charge across first capacitor? Q1 is equal to C1 into V. Q1 is equal to C1 into V. Similarly, Q2 is equal to what? Q2 is equal to C2 into V. C2 into V. So that implied, but this total charge Q must be equal to Q1 plus Q2. Total charge Q must be equal to Q1 plus Q2. So now I will find what is Q1. So Q1 is equal to C1 into V. That is equal to C1. What is V? V is nothing but Q by C1 plus C2. So that implied I can write Q1 is equal to total charge Q into C1 by C1 plus C2. Okay. Similarly, how can you find Q2? Q2 is equal to C2 into V. That is C2 into V. V is equal to what? Q by C1 plus C2. That is equal to Q into C2 by C1 plus C2. Now see, we know in a capacitance, in a parallel connection, voltage remains same. If voltage remains same, Q is equal to CV and V remains same for each capacitor. So that means Q is directly proportional to the capacitance. So Q1 is directly proportional to C1. Q2 is directly proportional to C2. So in this way, we can remember the formula. Okay, so this is the charge distribution in parallel connection. Now let us solve exercise 24.17. You see, there are four capacitors C1, C2, C3, C4. All capacitor value are same, that is 4 microfarad. And the potential difference across A and B is given 28 volt. So you have to find equivalent capacitance across A and B terminal first. So what will do? So now reduce the circuit. You see, this is my A terminal, this is B terminal. Here, these C1 and C2 are connected in series. So what is the value? 4 microfarad each. So this is 4, this is 4. Both are connected in series. So what is the equivalent? 4 and 4. So equivalent capacitance will be half of the individual. That is C1 into C2 by C1 plus C2. 4 into 4 by 4 plus 4. So that is equal to 2 microfarad. Okay. So C1 and C2 equivalent is 2 microfarad. And it is connected to, you see, it is connected to what? C3. C3 is nothing but 4 microfarad. C3 is nothing but 4 microfarad. And this, let us say this terminal is D. and from D to B there is another capacitor, that is 4 microfarad. So this is your B terminal. Okay. Next, these 2 and 4 are connected in parallel. So in between these 2 points, so here 2 microfarad, here 4 microfarad, both are connected in parallel. Then what is the equivalent? So equivalent is equal to, this is A, this is B, 2 and 4 connected in parallel. So net capacitance will be 4 plus 2, that is 6 microfarad. And this is D point. This is D point. So from D to B there is another capacitor, that is 4 microfarad. So now again you see these 6 and 4 are connected in series, because here A is connected to A and B is connected to what voltage? 28 volt. So here 6 microfarad and 4 microfarad are coming in one path. So 6 and 4 are in series. So I can write the equivalent capacitance across A and B is equal to C1 into C2 by C1 plus C2. 6 into 4 by 6 plus 4, that is equal to 2.4 microfarad. This is the equivalent capacitor. So this question was equivalent capacitance across A and B. So what is the answer? Answer is 2.4 microfarad. Okay. Come to second bit. What is the charge and potential difference across each capacitor? So now we will solve second bit. Question is, what is the charge across each capacitor? Now we see, we will find the total charge given by source. So what is the total charge? You see, the total Q is equal to CV. So what is the equivalent capacitance across A and B? That is 2.4 microfarad. Into voltage. What is the voltage? Potential difference, 28 volt. So just multiply this. You will get 28 into 2.4. I think it will come 67.2 microcoulomb. So now you see, this 28 volt is providing what charges? 67.2 microcoulomb. So this 67.2 microcoulomb will flow through this 4 microcoulomb. This is 4 microcoulomb. So here I can write here this charge. So here the charge value is equal to what? 67.2 microcoulomb. This is the charge. Okay. So here this is the charge. And same charge is flowing through 6 microfarad. That means this battery will give Q, total charge, is equal to how much? 67.2 microcoulomb to this combination. Now question was, what is the charge across this all the capacitor? So immediately we will write the charge across C4 is equal to what? 67.2 microcoulomb. Now you see here 67.2 microcoulomb is coming to this junction, and some charge will be flow through this and the remaining charge will flow through this. So here you see this is C1 and C2, both are connected in series. So here charge across C1 is also equal to charge across C2, that is Q1 is equal to Q2. But here what is the charge through C3? It is, let us say, Q3. Now how will you find the Q1, Q2 as well as Q3? Already we have got Q4. So what is Q4? Charge across this capacitance is equal to 67.2. Okay. So now what we will do, you see the B terminal and D terminal is connected across this capacitance, whose capacitance value is 4 microfarad and whose charge is equal to 67.2 microcoulomb. So now you first find out what is the potential difference. What is the potential difference across D and B? VDB. So V is nothing but Q by C. So VDB is nothing but QDB by CDB. V is equal to Q by C. So voltage across D and B is equal to charge across D and B. What is the charge across D and B? 67.2 microcoulomb divided by what is the capacitance across D and B? 4 microfarad. Now, so it is 16.8 volt. This is the voltage across D and B. Okay, you see, this is the voltage across D and B. Now, what is the voltage across A and D? So, voltage across A and D is equal to total supplied voltage. Total supplied voltage is equal to VAB. From that, you have to subtract VDB. That is, total supplied voltage was given 28 volt minus voltage developed across D and B is equal to 16.8. So if you calculate, it will come 11.2 volt. Okay. So now this 11.2 volt is this 11.2 volt is a voltage across A and D. This A and D voltage is equal to 11.2. Now see, this is your A point. This is D point means this is also D point. So voltage across A and D is equal to 11.2. Now what is the voltage across this capacitor? This capacitor 4 and these two are connected in parallel. So in parallel connection voltage remains same. So what is the voltage across this path? That is 11.2. Now what is the capacitance here? 4 microfarad. Okay, let us say you come to here. This is A point, this is D point. So across A and D, we got voltage 11.2. So here the 11.2 is the voltage, capacitance is 4 microfarad. You can find Q3. So what is Q3? Q3 is nothing but the Q is equal to CV. Q is equal to CV. It is C3 into VAD. So what is C3 value? 4 microfarad. What is VAD? VAD is 11.2. So you multiply this. So 4 into 11.2 is equal to 44.8 microcoulomb. This is the charge through this C3 capacitor. But what is the total charge incoming to this point? 67.2. Out of that, charge through this C3 is equal to 44.8. So remaining charge will flow through C1 as well as C2. So the remaining charge, that is either Q1 you can say or Q2, because these are connected in series. In series charge remains same. So Q1 is equal to Q2 is equal to total charge. Total charge is equal to what? Total charge is equal to 67.2. 67.2 minus the charge through this Q3 is equal to what? 44.8. Just subtract this, you will get 22.4 microcoulomb. So I got the charge across each capacitor. Okay. So now we will find what is the potential difference across each capacitor. Now see. So Q1 is equal to Q2, we got this value. Q3 is equal to this value. Q4 is equal to this value. So we have to find potential difference across each capacitor. So what is potential difference across C1? That is, let us say V1. So V1 is nothing but Q1 by C1. So Q1 is equal to 22.4 microcoulomb. C1 is equal to 4 microfarad. So you see, V1 is equal to Q1 by C1. V2 is equal to Q2 by C2. So both are same. So we got V1 is equal to 5.6. V2 is also 5.6. Then what is voltage across C3? Voltage across C3 is nothing but V3. V3 is equal to voltage between A to D. So that is voltage across A to D, which we have already got, or VAD is nothing but voltage across this C1 plus this C2. That is 5.6 plus 5.6, that is equal to 11.2 volt. Already we have got voltage across C4 capacitor, V4. So how will you find V4? Already we have got. Otherwise, total voltage is 28 volt minus voltage across these two terminal is 11.2. So if you calculate, you will get the voltage is equal to 16.8. Okay. So next, energy stored across each capacitor and total energy stored. So energy stored across first capacitor is equal to what? U1 is equal to half C1 V1 square. Similarly, so you know C1, you know V1, you can calculate. Similarly, you calculate energy stored across second capacitor, that is half C2 into V2 square. Everything you know, V2, V1, everything you know. You can calculate the energy stored across C3, that is half C3 into V3 square. And you can find the energy stored across fourth capacitance, that is half C4 into V4 square. Every data is given, just calculate, you can get. Then what is the total energy? Total energy stored is nothing but sum of individual U1 plus U2 plus U3 plus U4. Or you can say the total energy stored is equal to what? Half into V into Q. So half V. What is V? So V is equal to total supplied voltage, that is 28 volt. What is total charge Q? Total charge Q is equal to 67.2. So now calculate this, you will get total energy stored. So this total energy stored must be equal to U1 plus U2 plus U3 plus U4. So I am just giving hints, you just calculate. It is not. Now, what is the energy sent by the source? Energy sent by the source. So energy sent by source. Energy sent by source. So energy sent by the source is equal to V into Q. What is the total potential difference given? 28 volt. What is the total charge? 67.2 microcoulomb. It is volt. So whatever result will come, that will be in terms of microjoule. Then what is the energy lost? What is the energy lost during this? So energy lost is equal to total energy given is equal to VQ. Out of that, the total energy stored is equal to half into VQ. So the remaining energy is equal to half into VQ. So that is energy lost in the form of heat energy. Okay, with this I am concluding the session. So we have discussed the force between two charge parallel plates and the combination of the capacitors, and we have solved some numerical. In the coming class, we will totally discuss the various numericals basing upon the capacitance. Till that, enjoy your life. Okay, bye.